So we think of reaching out to you with Module 5, which deals with different topics like superconductivity, photonics, and optical fibers. As usual, what I do will be to give you a kind of overview of things, and your teachers will be hand-holding you through the lectures. So my sessions will be consisting of 3 short discussions. First discussion will be on superconductivity, second discussion will be on photonics, and third discussion will be on optical fibers. Coming to the discussion of superconductivity, I hope you all know that the solids in general are divided into 3 groups of things. First, conductors, and second we have semiconductors, and third we have non-conductors, which is also called insulators. Now we also know that free electrons are the charge carriers or the carriers of energy when we speak about conductors. And typical example is metals. We have abundance of free electrons which carry electrical energy. And in the semiconductors, you know that there is electron-hole pair, which is the charge carrier. They are paired, they are not free. Electrons or holes are not free, but they can be freed if you apply some kind of voltage. Now we come to discuss about a new group of material. They are not actually group of material, new state of matter, which are called superconducting states. So we cannot put them into the category of conductors, semiconductor, or non-conductors, but generally non-conductors are better superconductors at a given particular state. Now the discovery of this superconductivity was very accidental, and there is an interesting story behind it. A person called Onnes, his full name is Heike K. Onnes. He was doing an experiment in order to make a kind of measuring instruments for thermal energy or temperatures, especially at very small temperatures, which means temperatures near to absolute zero. In those days, it was very difficult to measure temperatures near to the absolute zero because there were many complicated machines. So he wanted to simplify everything. And based on a simple principle, which speaks about the variation of resistivity with respect to the temperature. As you know, according to the Ohm's law, or as a corollary of Ohm's law, you know that you expect a curve which is moving to like this, which means that if at a higher temperature you have a higher resistivity. As the temperature decreases, the resistivity will be decreasing. And classically it is expected that even at 0 Kelvin, we do not expect this resistivity to completely fall to 0. This gives a good idea of making an instrument which could measure the temperature with respect to resistivity, variation in resistivity. So the purpose of this experiment was to understand how the resistivity comes down as the variation or as the lowering of the temperature. And the man, the lab assistant who was doing this experiment, found something absolutely amazing. He found that at a particular temperature, which is later on called a critical temperature, this was approximately 1.15 Kelvin, something interesting happened, which he could not really understand that particular time. The resistivity just fell down. Instead of following the classically expected path, it was just coming down. So this particular observation, he just first thought this could be some kind of mistake in his experiment. And he was repeating this experiment, this lab assistant. But then when he found that this is the case all the times, he reported that to Onnes, and that was the Onnes had the insight that this could be a new phenomena, and this new phenomena was later known as superconductivity. You can see, as you see, the resistivity of the material falls down to 0, which means the conductivity of this material becomes infinity at a particular temperature and below that particular temperature, which is called a critical temperature. I should tell you why this is this particular expectation of residual resistivity at small temperatures or even at absolute zero. You know, this all understanding comes out of a theory which describes the flow of electrons or the conductivity as due to free electrons. As I mentioned earlier, a lot of free electrons in a metal. In this particular case, it was mercury, a liquid metal, as you know, and they were doing the experiment on mercury because you know, a thermometer is usually thermometers are generally made out of mercury, and that's the reason they experimented with this. Even at a very small temperature, even at absolute zero, we expect some residual resistivity because of the expected impurities or dislocations and defects in the crystal structure of this particular metal or conductor. But this particular observation, which means that below a particular temperature, this resistivity falls to zero or conductivity becomes infinity. This was a totally new observation, which of course for the lab assistants looked like a mistake because they could not make any more a thermometer because the measurement between this particular TC and zero is never possible. So their project is failed. So out of a failed project, there comes to a beautiful understanding of a new state of things at a low temperature, which can be called superconductivity. Now, this happened in 1911, and even 2 years later, maybe this is a very rare thing in the history of Nobel Prizes. They got within 2 years they got this particular man, Honest got Nobel Prize for this particular discovery because the whole world understood the importance of this particular discovery. Now, there were many researchers doing further research on this. And another German engineer who did experiment on this effect was Meissner. And he did almost the same experiment, excepting that he was doing the experiment under magnetic field. So he applied a magnetic field over to the mercury sample and was trying to understand what is happening with the magnetic field within this material, mercury material, when this material was cooled below this particular critical temperature which we mentioned already. So it was found that before reaching this particular temperature, you know, all the force lines due to this external magnetic field which is characterized by H was passing through this material, just passing through this material. But at critical temperature, as the critical temperature was reached, he found something amazing, that these particular force lines were all expelled from this material, making the field inside this material to be zero. You know, generally you should understand the field within material is represented by an equation B is equal to mu into H plus M, where H is the magnitude of the applied field and M is nothing but response of this material towards this field, which is called magnetization. So there will be two components for the field, H and M. And when we found that this is equal to zero, you know, mu cannot be zero. So H should be equal to minus M. That is understanding. So H is equal to minus M, or if you find the magnetic susceptibility, you can see it will be M by H. So it will be minus, these are equal, so there will be minus 1. So this is the maximum susceptibility a particular material can exhibit. So this is the sign of perfect diamagnetism. You know, usually the magnetic material will have different types of responses to an applied magnetic field. You have heard about that earlier, already in the smaller classes. When this material is paramagnetic, this will be a small positive value for M, and therefore B will be slightly enhanced than H. So that phenomenon is called paramagnetism. You know, slight negativity of opposing of this particular magnetization to this applied magnetizing field. This is called diamagnetism. A slight rebellion But here, the rebellion is absolute rebellion. See, if you draw a curve, for example, between applied magnetic field and magnetization, you will find a amazing thing. If this is a applied magnetic field, or this is the magnetization corresponding to the applied magnetic field, we see a kind of curve which is can be drawn only in the minus axis, negative axis, the fourth quadrant of this particular equation. Or if you put minus here, you can even draw a graph which could be drawn in the first quadrant itself, which will be showing you a kind of graph like this, which means as you increase the applied magnetic field, there will be a negative magnetization in the material, which is exactly equal and opposite to making this field inside zero. This effect was called Maestro effect after this inventor. Now therefore you have a comprehensive idea about two parameters which could influence the onset of superconducting state. There is, on one hand, you have temperature. So you have temperature, and on the other hand, you have a magnetic field. So both magnetic field and temperature, they are two independent parameters which will determine whether you are reaching a superconducting state. Therefore, you can imagine, you can draw a particular graph like this, where you have, you can put this critical field here, and at this point you can put the critical. This is generally it is H, but this particular point you can mark as HC, the critical field. You can imagine that the definition of critical temperature is made under zero field, and similarly the definition of the critical field is made at 0 Kelvin. Now, let's imagine more increase in temperature, what will happen? Which means the temperature reaches, for example, let us say temperature is, rather you apply a magnetic field which is of this particular value, then you can imagine there will be a corresponding requirement of cooling this particular HC1, TC1. To cooling much more closer to, much deeper cooling is required. So the material should be cooled towards near to this particular temperature. So if you apply a greater field, for example, you can see similarly the cooling requirement will be much more. So like this. So this is the understanding which we should have. So there is a curve, and below this curve, you can imagine this particular material will be electrically superconducting and magnetically Meissner. So this material will be electrically superconducting, which is infinite conductivity will be there for this material, and magnetically Meissner, which means this material will exhibit perfect diamagnetism. So this phenomena is what is called superconductivity. So you can imagine this phenomena is controlled by thermal energy as well as magnetic energy. So magnetic energy and thermal energy together make this kind of phase change. What is outside here? All region outside can be called normal state, which means electrically, normal state means electrically the material will obey the Ohm's law, which is a very famous law controlling this conductivity. And this electrically normal and also magnetically the material will be normal. Means its normal behavior, magnetic behavior, let it be paramagnetic or ferromagnetic or ferrimagnetic or diamagnetic, the original behavior, magnetic behavior will be exhibited here. But within this particular state, below this curve, this region will be characterized by, if material reaches this region, the material will be electrically superconducting and magnetically perfect diamagnet, which we can say magnetically Meissner. So this is the phenomena of superconductivity. Now, people always thought, why should it happen like this? And the answer to this question was given by a group of scientists, which is called Bardeen, and the theory is named after them. This is B stands for Bardeen, the first scientist, Cooper, and Schrieffer. These are the three. So Bardeen, Cooper, and Schrieffer. So the scientists together develop a theory to explain why this happens. So why is very important question in physics. It's not just understand some phenomena. We should be able to say why this happens. So the heart of, as it stands in the middle, the heart of the theory is given a concept developed by the Cooper, and he developed an idea about Cooper pair. So this is an interesting pair of fundamental particles, which we should really understand perfectly if we have to understand the phenomena of superconductivity. It is actually a pair of two electrons with equal and opposite equal charge. Of course, electrons will be having equal charge, but opposite momenta and spin. So you can represent maybe like this also. So electrons with equal charges, equal charges means, generally you don't expect equal charges to make a pair, because like charges, as you know, in electricity, they will be repelling each other. So they want to stand as apart as possible. But according to this theory, there's a special, unique occasion where these two electrons, even though they are like charges, can make pairs. And that particular name for this particular pair is the Cooper pair. So this is the Cooper pair, a pair of two electrons, which can be the reason for this particular phenomena which we call superconductivity. So how to explain all the two important phenomena, the Onnes effect and Maestro effect, which you have already found, based on this Cooper pair, is the next task we should think about. How this Cooper pair is formed, that is the first question we should ask. According to this theory, if two electrons are standing at maybe at a 1,000 Armstrong distance, which means distance of about 1,000 positive charges, nuclei, which is devoid of electrons. So you can imagine there will be many hills of this, potential hills of this constituted by these particular positive charges. When electrons are freely moving, you can expect a large number of positive charges, which is small hills, potential hills. And these are two electrons sitting, or a large number of electrons flowing through the valley of this particular hills. What happens according to the Cooper is that this particular large number of electrons flowing through one side of this particular hill will be moving, bending all these positive charges towards this negative charge. So it will be attracted like this, because positive and negative charge will attract, and here again they will attract towards that, so it will be oscillating. When the system is oscillating, we say that there are phonons are created. So these are the condas of lattice vibration. This positive charge is called lattice. So lattice will be vibrating and phonons will be created. So phonon assisted electron pairing. That is what is the understanding about a Cooper pair. So how Cooper pairs are formed? The Cooper pairs are formed by phonon assisted. Phonon, as I told you, is the conda, the smallest unit of this lattice vibration. And all these phonons will be making a cloud over these two electrons, and they will be combining these two electrons into a pair like this. So these electrons will be having up and down spin, and the momentum will be also in the opposite direction. So two electrons with equal and opposite momenta and spin, they create this particular system, which is called a pair of Cooper pairs. Now, this is really interesting to understand how these two phenomena really happens. Let's imagine a phase change. Let's draw a diagram for energy level diagram for a phase change. Let's imagine this is the threshold value of temperature or magnetic energy required for breaking this particular superconductivity. As I have not mentioned that to you, another part of this experiment is that when you add thermal energy or magnetic energy, this superconducting material will be automatically becoming normal conducting material. I have mentioned to you through the graph that below a particular curve, area under the curve, which will be defining this superconducting phenomena, and beyond that curve everything will be normal. So in the normal state, conductors will be having large number of free electrons, And I intentionally draw an energy level diagram for free electrons to be like this, because you know electrons belongs to a group of particles which we generally call fermions. And fermions are, so let me write that, fermions. Fermions are those particles which will obey Pauli's exclusion principle. And you know what is the Pauli's exclusion principle? It just means that two such particles which are called fermions, which will obey Pauli's exclusion principle, they cannot occupy the same energy level. That is why I have intentionally drawn different energy levels for different electrons. So electrons are fermions, and fermions, electrons which are fermions, they are the charge carriers in the case of normal conductor. So this region is called normal magnetic behavior region. And now, when you remove thermal energy, when you remove magnetic energy, the material will form, this particular conductor will form so-called, what's called Cooper pairs. Now, there will be, this particular region will be all filled with Cooper pairs. Now, you should know what is a Cooper pair. What is the fundamental nature of the Cooper pair? Cooper pairs are not fermions, which means they will not obey Pauli's exclusion principle, which in other words means, so these are, they are bosons. The bosons are those fundamental particles which will not obey Pauli's exclusion principle. If you remember, our lab is known as the physics lab is known by the name boson lab. And now the reason is that there is a particular boson which we are discussing, example for boson, another example for boson, and you know what is that? It is photons, the light, the quanta of light. Now here we have a second example for bosons. Bosons are, again I repeat, they are the particles which will not obey Pauli's exclusion principle, which means that large number of these particular Cooper pairs can occupy one and the same energy level. So what happens when we increase the magnetic or decrease the magnetic or thermal energy, when we move from normal conducting to superconducting state? So this is normal state, and this is, I put it here, this is superconducting state, superconducting state. These are bosons, I mean this pair is a boson. So you see, actually the transition, when you remove heat energy or magnetic energy from this system, what happens is that these electrons will not be the charge carriers anymore. Instead, you have a new type of charge carrier coming into play, which are called Cooper pairs, and Cooper pairs are bosons. By saying that they are bosons, you should understand large number of them, they do not obey Pauli's exclusion principle, which means that large number of them can occupy same energy level. So this is just like you know, a one particular level where the large number of them can sit together. So they just move without requiring a voltage. So this is a you know, this particular region, normal region, the current, you know, current is flow electrons in this case. Current will be moving, which for the movement of current, which requires, as per the Ohm's law, a voltage. But here, this region is voltageless current, so the current will be driven without needing any voltage, any potential difference. So which means, you know, they will be acting like a superfluid, and they will be just flowing without requiring any driving force for them. So this is what is called, you know, this is what is called superconductivity. So a voltageless current. Basically, superconductivity is a voltageless current. We'll come to know that in detail later on. So a voltageless current is possible. A current can be there, which will be, you know, in this particular normal region, normal state of the material, you know, electrons, you can see that electrons has to climb different steps of a ladder, energy ladder, which requires a lot of expense. So, and there will be resistance for that. Here there is no resistance. So, superconductivity, which means without resistance, a flow of electricity, flow of electrical energy, without need of any assistance of any external potential difference is possible, because these particular charge carriers, which is called Cooper pairs, do not experience any amount of resistance. So infinite conductivity or zero resistivity can be explained based on this particular understanding. Now, next question is how can you explain Meissner effect? Now, Meissner effect, as you know, is an effect which is simply said it is a perfect diamagnetism, which means this particular system of Cooper pairs will be opposing, absolutely opposing influences of any applied magnetic field onto it till a particular limit. You can see by looking at this diagram, what will be what will be demanded by an applied external magnetic field by this system of two oppositely oriented magnetic moments. Of course, this particular external magnetic field will want this kind of structure, which means they are aligned in the direction of this external magnetic field. But to align in the direction of external magnetic field is a life and death problem for this particular Cooper pairs, because they will be broken. Because they are defined as basically defined as two electrons with equal and opposite momenta. And if the magnetic momenta has to be aligned in the same direction of the external magnetic field, they are no more. They are dead and gone. So therefore, there will be a life and death struggle for these Cooper pairs. They will oppose any kind of change demanded by external magnetic field. They will not want to change. But when it reaches a critical value, of course, they will have to align. So that is what is called a critical magnetic field. If the critical magnetic field is reached, the magnetic energy is such great or beyond this particular critical magnetic field, they will be losing their identity as Cooper pairs, and thereby they will be losing this perfect diamagnetism, which is characteristic of a Cooper pair, which is characteristic of a superconducting state. So as I told you, this basic idea about superconducting state, that they are honest, they have an honest effect and Meissner effect. They are completely explained by BCS theory. By just defining a quantity, a new quantity which is called Cooper pairs, this will be sufficient to explain both this particular idea. Now, you should understand one important thing. You should not confuse yourself by thinking just because these superconductors are having infinite conductivity that they can carry any amount of current. It is simply not possible. I can explain it in a simple way. Let's imagine we are making a wire which can carry a lot of energy, electrical energy. Let's imagine you make this out of a superconducting material. Then you can imagine that there's no resistivity for this wire. So you may think that infinite amount of current can be carried by this wire. Absolutely wrong. It cannot be, because that when the current is carried by a wire, a conductor like this, a superconducting conductor like this, there will be associated magnetic field developed. Now, if this magnetic field reaches a value greater than Hc, which means this superconductivity of this material is gone. So this wire becomes a normal conducting wire, and therefore you cannot carry infinite amount of current. Because of the limitation of the Hc, you cannot carry large amount of current. Therefore, we should, the materials like mercury or other similar materials which was originally discovered, they are exhibiting perfect electrical conductivity and perfect diamagnetism. They had a simple problem. The problem was that this critical field was very low, generally below 1 Tesla, which is not sufficiently high to carry large amount of current through these wires which can be made out of superconductors. So they are technologically insignificant discovery. This is only theoretical curiosity behind that. Therefore, people start developing new type of materials which can have this kind of properties, and type 2, different types of superconducting materials were high temperature superconductors are discovered. As I told you, the fundamental thing remains the same, which means there will be a critical values, a critical value in temperature as well as in the magnetic field, beyond which the material will be completely perfectly superconducting. Plus, this will be also Meissner. So, which means This will be also exhibiting perfect what's called diamagnetism. But there's a certain type of, a new type of material which can be called type 2 superconducting materials. It was found that they are having another behavior. They are having a region which we can call the mixer region. So this is what is called mixer region. And the property of this mixer region is that the material is electrically superconducting, but magnetically not Meissner. Which means perfect diamagnetism is not exhibited by this particular, below this particular, there's a second critical field. I just break it. I will tell you the reason why I break it. Because, this will be at least 1,000 times, HC2 will be at least 1,000 times above this HC1. Therefore, I'm not drawing this graph according to the scale. That's why I break the. But, more importantly, what we find here is a interesting type of materials which will be having two critical fields. Below HC1, the first critical field, the material is electrically superconducting and magnetically Meissner, which means it's a superconducting and perfect diamagnetic. But in this region below, between this HC1 and HC2, critical temperature being the same, you find there's a material is superconducting, but there's no perfect diamagnetism, which means the material itself allows the magnetic force lines a little bit into this material, but superconductivity, electrical superconductivity is maintained. And now we have a normal region beyond that. So there are three regions right now. This is superconducting and Meissner region. This is below SC1. Between SC1 and SC2, you have a mixer region where the material is superconducting, absolutely interesting, but it's not perfectly diamagnetic, does not matter, because what we look for is a high value for SC1 in order to allow large amount of currents to be carried by a wire which is made of superconducting material. Because these superconducting materials are the first primary applications in the technical field was to make maglev technology, magnetic levitation. Which means large mass will be like a metro wagon, will be lifted by this particular powerful magnet, which will require large amount of current to be passed through this particular superconducting wire, which is allowed only by HC2 having higher value. If it's not having, for example, it's having 100 Tesla, let's say take a value like this. So you can imagine large amount of current, superconducting current can be passed through this particular conductor without losing its superconductivity. Of course, Meissner effect will be compromised. The material will not be anymore having perfect diamagnetism, but this material will be still having superconductivity. So you can have, for example, another example will be MRI, where we use Tesla, high Tesla value MRIs, 4 Tesla, 2 Tesla, etc. That requires we want to make sure that large amount of current can be carried by this wire made of superconductor. This is possible only with the type 2 superconductors. So this is the typical behavior of a type 2 superconductor. There will be two critical magnetic fields, and generally HC2, the second value, will be very high, allowing you to carry large amount of currents in order that you can make really super magnets which can be used inside MRIs or also for, as I told you, maglev technology. Now, this is all about the classical understanding of superconducting materials. Now, I take you to a new area. Most of you are electronics and communication students, so for you something really, really interesting I'm going to speak about. There was a professor, I have told you large number of experiments are being conducted, with this being a hot area, very new area. He made a particular junction. He had one superconducting material, second superconducting material, and sandwiched by a insulating material. And this name was Anderson, and this professor was doing experiments on this. And on one fine day, he found that when he connected this a galvanometer, and he cooled this particular system, which he did not name at that time, he wanted to cool it below a critical temperature. Now something amazing happened. This was having a very small thickness, for example, let's say thickness of 100 Armstrongs, very thin insulator. But you know, these are two superconductors, but sandwiched by an insulator, which means that you don't generally expect the currents to flow through this junction because it's an insulator, perfect insulator. But for his great surprise, he found that this galvanometer is moving when this material was cooled below Tc. And he explained this to his graduate students in physics in this class. He put it as a homework. Can you think about why it happened? Can you explain why it happened? Now, there was a very genius student. This happened in UK. There was a student sitting there whose name was Josephson, and he took this challenge and he did developed a beautiful theory as a part of a homework. The homework was taken very seriously by him, and he very next morning he brought this professor an equation, which is a path-breaking equation, my dear students. He brought an equation which just said the current flowing through this particular junction will be a constant current and a sine function of del. And he assumed so much of things. He assumed that there are Cooper pairs in, as I told you, Cooper pairs are the reason for the superconductivity. In both the superconductor 1 and superconductor 2, there were Cooper pairs, and here the Cooper pairs had the pace theta 1 and here pace theta 2, and del was defined as theta 1 minus theta 2, the difference in pace between these wave functions. You know, there's a new concepts coming in. You know, every small particles, as we have studied in quantum mechanics, can be expressed through a wave function. They are not particles, they are at the same time particles and waves. That is why the wave function of this particular Cooper pair will be having a pace of theta 1, and the second one will be having theta 2. Just imagine that and this del. So you can imagine the constant current, even though there's a sine function here, this is a constant value because this is fixed, theta 1, theta 2 are fixed. So you have a constant current will be passing through this particular junction. My dear students, this is what is called later on known as Josephson junction, and this is Josephson DC effect, which just means that if you have two superconductors sandwiched by the insulating region, and when this system is cooled, a DC current will flow through this particular junction. And he explained through a particular phenomena which is called quantum mechanical tunneling. Tunneling of this particular small barrier, which is insulator barrier, by superconducting wave functions. So when we consider these particles as waves, they have a finite probability of tunneling any barriers. So this is seen in many cases, and he explained this for the junction between Josephson junction. This is later on known as Josephson junction between two superconductors sandwiched by insulator. My dear students, the beautiful thing about this story is this is the birth moment of a new branch of electronics. You know, in the normal electronics, you have p-n junctions as the fundamental element. But here you have a new electronics which can be called superconducting electronics, where the fundamental element is a Josephson junction. This was later on known in the name of the student, not in the name of the teacher who initially did the research. You know, because Josephson could develop this particular equation. Now, you can imagine this particular equation is a Nobel Prize winning equation. He was one of the youngest physicists who won the Nobel Prize. And the Nobel Prize for this particular equation, and you know, we said that you can assume, you can consider this superconductors made of Cooper pairs, and Cooper pairs having different paces, and you can define a current just flowing through. Even when there is an insulator, due to quantum mechanical tunneling, some current will be flowing through this particular circuit, and this will be known as DC Josephson effect. Now, as you can imagine, there will be further experiments on this. So the same junction, which is called superconducting, insulating, and superconducting Josephson junction. Now, let's imagine you are giving a kind of DC voltage to this particular system, which we can call Josephson junction. Now, something totally amazing happened. They found that, you know, this particular current starts oscillating. Oscillating at it's an AC. This becomes of course, you have given DC here, but the current get oscillating through this particular junction, and it became AC, not only just an AC with a tremendous value for its frequency. So the frequency was defined as 2eV divided by h. H, you can imagine, h is having 6 point some value into 10 raised to minus 34, and electronic charge 1 point something into 10 raised to minus 19. So you can imagine this will be, depending on the voltage, it will be having minus 34 in the denominator, minus 19. So it will be of the order 10 raised to 15 hertz. My God, this is amazing, because such a frequency is not found in any AC. So 10 raised to 15 million gigahertz. You should compare this with your ordinary laptop. It may be having maybe 3 gigahertz. That's its speed. Basically, the speed of an electronic device will be determined by the switches inside. So we are defining a switch-like system here, which is basically made of Josephson junction, which can create a tremendous value for its frequency. So you can imagine this will be improving your future computer, the quantum computer. If this particular junction is applied there, you can imagine this will be improving its quality or its speed by million times. No, such a big value you cannot really expect in technological world, but this kind of improvement can be given. This is what I told you. This is a birth moment of a new branch of electronics, which can be called superconducting electronics. Superconducting electronics is having great promises. As I told you, it can give you high frequencies, high switching speeds. Devices will be faster, working faster when you apply this particular superconducting electronics. And something which I want to mention and conclude my session is about SQUID. SQUIDs are conducting quantum interference devices. I don't go to details. I'm not supposed to know detail. You can research and find what does this mean. I just give some quality of this particular device. This particular device is a magnetometer, which means something which measures the magnetic field and measure the magnetic field to the range of 10 raised to minus 15 Tesla. A small magnetic field it can measure. For example, when you think with your brain, there's a magnetic field maybe approximately 10 raised to minus Tesla. This can be captured by this particular cute device, which is called a SQUID in short form. Similarly, when your heart is moving, beating, it will be again creating not only love, also some kind of magnetic effects are created, and that can be in the same range. Biomagnetism, magnetism of your brain, magnetism of your heart, magnetism of your stomach when it's digesting something. All this can be measured, and this could be beautiful devices because they measure things such a precision. And you should imagine this is one of the most precise machine human hands have ever made so far. So that is the beauty of superconducting electronics. Now we have a new branch of electronics which you can call superconducting electronics, where instead of PN junctions we have Josephson junction. Josephson junctions replacing PN junctions. And Josephson junction, as I told you, is just a junction between two superconductors sandwiched by an insulator. So you'll have a lot of fun in studying this superconductivity. And I told you a lot of promises superconductivity is giving the humankind. MRI, microwave technology, SQUID, or high-speed quantum computers. All these are the new and bright, promising field of technology. And if you really understand superconductivity, there's also a chance for you to win a Nobel Prize. Maybe I conclude by saying that. And even though I mentioned type 2 superconductors, there's reason for type 2 superconductors are not perfectly the theory behind why this happens, why this critical magnetic field occurs. This is not properly explained. So I am pretty sure that if BCS theory, which explains the type 1 superconductors, got Nobel Prize, I can assure you that you can also win a Nobel Prize if you develop a theory for type 2 superconductors also. Thank you so much.